Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This is work mainly done by Nicholas Heason and Danny Tyler, who's going to be talking next, but I thought I'd take the credit for it. So what we're going to be talking about today is, I'm really excited about probabilistic programming. I think it's a sort of really powerful way of doing machine learning, of building very rich and complex models. And so what I'd like to be able to do is build massively complex models, prodigious models in probabilistic programs. But then the problem is, at the minute, such things, we cannot actually execute those probabilistic programs. We cannot do inference. And so the question is, how can we persuade prodigious probabilistic programs to be somewhat plausibly performant? I got that off. Phew. Okay, so who knows about probabilistic programming? That's pretty much everyone. That's great. Okay, so we have our own kind of in-house probabilistic programming language. We have our inference engine compiler called infer.net that we've been working on for 10 years this month. And here's an example of the underlying programming, probabilistic programming language that it uses, which we're calling probabilistic C#. So it's just C# with the addition of some random operators and some other operators that I haven't shown here. And this is just a base point machine classifier implemented as a probabilistic program. Perhaps a more familiar probabilistic programming language to many as a functional form is Church. So here is a Dirichlet process written up in Church. The exact choice of program here is random, just to illustrate the differences between the two. So what we'd like, let's look. You have these two different languages which obviously express the model in two different ways, but they also have two different ways of doing inference on these programs. So let's look at that. So how does inference work in infer.net? So it's based around deterministic message passing. And in order to make that work, it needs to be aware of a large set of, built-in message passing operators for factors like plus, minus, multiply, and so forth. And we support expectation propagation and variational message passing to do that. But in order to make this message passing algorithms work, we need to have a very detailed understanding of the probabilistic program. We need to know about every single function that gets called. We need to know about every single variable and how it's connected to every other variable. We need to know about every if statement and function call. So we need an extremely detailed understanding of the program. The advantage of this is that we can then pass messages up and down that program in either direction. Let's contrast this with Church and the family of Church languages. So here, inference is done by various sampling approaches, and there's been a mass of them that I won't attempt to summarize on one slide. But crucially, the program is treated as a black box. It's essentially only run forward. Likelihood-free is a term for that. There's some more recent work that uses the dependency structure, but really it's trying not to know and not to understand too much about the program in detail. And this is great in some ways, which I'll get to in a second. So the program is only run forward. So let's look at the pros and cons of these two approaches. So let's start with the pro of infer.net because it's home territory. Infer.net is fast. We've run it on terabytes of data. It's deploying on large-scale server farms. I mean, this is sort of seriously scalable stuff because it's able to essentially reproduce the sort of hand-coded machine learning solutions that you or I might code up. And the advantages of Church that are super exciting is that you can use any of your programming language elements. So you have a super rich modeling language. You can build some incredibly exciting things. But with these huge advantages come disadvantages. So as I've sort of suggested, Infer.net can only do inference on stuff that it knows about. So if you want to do something new, like, say, fit an ellipse to some points, and let's just see if Andrew's awake. Yeah. And you don't have the cosine function built in, then you're sunk. I mean, you can add it yourself, but it's a lot of work. In contrast, Church will have no problem writing such a program, but then it's very slow to run. Because essentially, because you're only running forward, my crude understanding is that because you're only running forward, it's very difficult to determine what sort of parameters of your program are likely to give rise to particular data in high dimensions. So the question is there some way we can get the best of both worlds? Could we get really fun, funky, rich probabilistic programs to run on large scale and at high speed, which I think would be extremely exciting. So here's an idea that I'm hoping might go in that direction. So the idea is we mix the two things. So what you see here is a sort of infer.net factor graph. And then we're going to have this red factor in the middle. But the red factor is not going to be defined, is not going to have message operators defined for it like all the other ones. So let's assume all the black ones are things that infer.net already knows about. And so we know how to pass messages in the rest of this graph, but here we don't. So rather than sort of writing a program for the whole thing, we'll write a program just for this one factor. So here we're going to have a throw a ball factor. And so what it's going to do is it's going to take in the velocity, angle, and height of someone throwing a ball, and return the distance that the ball goes. So it's a fairly simple little function, but it would be quite a nightmare to code up as a factor graph. So this one slide will tell you the whole story, and then I'll go into as much detail as I have time for. So step one, then, is we define an arbitrary new factor to put into our factor graph via a forward program. What we're going to do is we are going to use the same sampling methods of the Church family of languages, essentially, to compute the messages going from the factor in all directions, up and down. And this is going to take a while. So this is the slow part. But what we can then do is treat those messages as a training set for some really nice, fast regressor, like, for example, a neural net or random forest. Okay? So whilst this may take, well, not quite Andrew's billions of years, but this, you can stick this off on a cluster of 1,000 machines for a while. What you'll get is a training set that you can then train a regression model on that will be extremely fast. And then you can use it. So then you can run inference in the entire model, and it should be fast and scalable. Zubin.
So you need the regression model to be able to actually compute the messages in all different directions,
yes,
from all combinations of the inputs,
yes,
of the other.
Yes. So actually, it's a regression model per outgoing message. Okay, so let's dive into a little bit more detail. We're going to look in particular at expectation propagation. So here, we have our throw a ball factor, and we have some messages coming into it, and we need to know the messages going out from it. In particular, we're interested in this message for this slide. So the messages that are coming in are just little distributions, like here. And then EP tells us to compute the outgoing message, we need to compute this quantity. So for those of you not familiar with expectation propagation, we're basically multiplying together all the messages that are coming in, multiplying by the factor function, and then projecting this onto the family of outgoing messages that we want, and then dividing by the incoming message on that edge. Okay? So what we're going to actually do is train on this top part before the division. So this quantity, as I say, for each of the operators in Infer.net, somebody, usually Tom Menke, has gone and carefully done the numerical integration to implement that equation. But as I say, we're going to learn to do it instead. Okay. How long have I got? Okay. All right. So in this case, we're just going to use the simplest possible form of sampling, importance sampling. But you can plug in better samplers. In fact, all the rich sort of sampling ideas coming from the church community could be plugged in at this point. We'll just use importance sampling. And so all we're going to do is we're going to take the incoming message to the factor. We're going to sample from those messages. And then what we need is a proposal distribution. So, sorry, I've jumped a step. So we've got a proposal distribution. The simplest proposal distribution you could think of is just to sample from the messages. And we'll show that that can work. In some cases, you might want to change that proposal distribution. And then we're going to be able to compute this top quantity as an expectation of those sampled messages, a proposal distribution multiplied by this, which we can't compute, but we're only going to sample from. Is that clear? I've got a picture. So just before I get to the picture, though, so what we're going to need, though, is we're going to need a whole representative set of possible input messages that could arrive at this factor so that we can train on it. So we need something to kick that out. So we're going to hand-pick some broad distribution over messages that's going to say what messages arrive at that factor. All right, let's have a picture of this. So here are the 4 incoming messages to this factor. And so step 1 is we sample from the messages going in. So there are some samples from the messages going in. Then step 2 is we take those messages and we pass them through the factor, and so we get samples from the output of the factor. And then we compute the important sample weights based on the inverse message. And then so what you can see here is we've reweighted the samples, in this case for this message. Then you can reweight the samples up at the top, in this case for this message. Then you can take the resultant set of samples and fit the appropriate family distribution to them. Okay. Now this thing exists already. It's called ABCEP. And obviously, it works fine if you can make this step work. But the crucial additional step is that you then train this very fast procedure to replace this slow sampling step. Okay, so let's look at some examples. So what we have here is where we've taken the logistic factor and replaced it by a short piece of code that computes the logistic function. We have the logistic factor already built in Infer.net, so let's see how they compare. So what we have here is we ran it inside a logistic regression model. And what we have here is the KL divergence, the log of the KL divergence between the true backwards message, or at least the one computed by the Infer.net hand-crafted operator, and the learned one. And what you'll see is this is the log KL, it's generally extremely small. In fact, if you look at these points, at 1, 2, and 3, the two curves are indistinguishable. And at the very worst point, they look like this. So that occasionally it goes wrong. And for the forward message, this is the very worst approximation. So on the whole, it seems to have captured automatically what it took, several months of work to code up by hand. And so we can then use this in a model. So let's put it into our logistic regression. So we'll get some artificial data just to test this out. And what you find is that the test accuracies with the neural network are essentially indistinguishable from the test accuracies with the hand-coded factor. So that's nice. Zubin.
Sorry, going back to your previous slide, I just wanted a bit of clarification. So here, what you've described is the important sampling procedure that you would need for one particular value of the incoming messages.
Yes.
And so you need to actually repeat that
Yes.
for
a
many,
large
many,
representative set of messages. So this is why this takes a while. Yeah.
And
So
the mapping is from message parameters, basically, from actual messages
from
to actual messages.
actual messages to actual messages. So sorry if I wasn't clear.
It's a low-dimensional
Yeah.
mapping.
So you might have like 1 million examples of incoming messages,
Yeah.
and the corresponding outgoing message, and then you're trying to learn that mapping from message parameters to message parameters.
And for most, I mean, you could put in wacky factors, I guess, but often that's kind of a nice, well-behaved mapping.
The assumption is that it's a well-behaved mapping, that in some sense, even though you will have this sort of rich, complex program, that mapping is going to have lower statistical complexity that can be picked up by a suitable function.
I mean, in particular, because even if you have very abrupt things in the mapping, you're smoothing over them by having randomness in the income. I mean, the messages are distributions and so.
I think you still need to have abrupt changes in the mapping. That's something we're still investigating. I actually cut that bit, but I can talk about that offline. But that's why I think random forests might be more useful than neural nets, because they're better able at having sort of more abrupt sort of phase changes in the mapping. But I can show you some mapping pictures in this. Okay, and similarly on real data, the test accuracy is slightly lower, but only very, very slightly. It could be within noise on the one of the classic UCI data sets. Let's look at another factor. So this is the compound gamma. So another example of why this is useful is that in infer.net you have these sort of building blocks, plus, minus, times, Gaussian. And you're running a sort of factorized variational approximation on these. And so if you could somehow merge them together, you'd get a better approximation. And so here, the compound gamma is actually a small structure in the graph. It's a gamma pointing at a gamma. And this gives you a nice heavy-tailed distribution. Sorry, jumping ahead. And so this is a very useful thing to have in your modeling toolbox. And we can replace that whole graph structure by a single factor that does the same thing. And so there's this other sort of potential, which is, as well as automatically getting sort of new factors, we can take existing sort of sub-chunks of the graph and replace them by one factor, and hopefully improve our inference accuracy. So here's a point I want to make about this factor. If we use the Q distribution, that was the proposal distribution for samples, that was just a product of the incoming messages, then we can sort of miss bits. So here, this is the log of the sum of importance weights from the importance sample, which is an indication of the quality of your samples. And you'll see that there are sort of gaps. If we robustify that proposal distribution a little bit by broadening it out, essentially a mixture of the original with a broader version, then we can overcome that problem, which is shown down here. And if we look at the message surfaces here, so what you basically want to see is that in this case, the robust, this is the shape and rate coming from the robust importance sampling, and then the corresponding shape and rate as predicted by the neural net. And the black dots show where, for a typical experiment that we ran, the values that were actually used. Okay. I'm going to skip to the ball thrower for the final minute. So we started with this. So here is a nice example of putting in a custom factor, the ball throwing factor, inside a model. We also built a regression version of this. So here we have a bunch of people, n people, each throw a ball t times, and we want to know their sort of underlying typical velocity, angle, and height that characterize how they throw balls from the 3 examples. And so what we have here are, after 1, 2, 5, and 10 observations, for 2 different people, how the posteriors for the learned factor compare to important sampling in the entire model. And you'll see that they're matching up. Obviously, this took much longer. If we, oh no, I don't have that. If you penalize important sampling to have the same compute budget, it does much worse. Okay, so this is maybe not be prodigious yet, but we're heading in the right direction. So what we're very keen on doing next is exploring random forests instead of neural nets. The other thing is, at the minute, you have to sort of say what the distributions over messages are, but you can imagine doing this in place. So imagine you just create this factor, you actually want to use it, you stick it in your model. The first few iterations are incredibly slow when it does this sampling. And then it's got enough to learn the fast regressor, learns it, and suddenly everything goes fast. And it will go fast from then on. And I think that's sort of almost human-like. Like when you start doing a task, it's slow, and then it gets faster. And, as I say, the goal then is to try it on larger and more prodigious probabilistic programs. Thanks.